All right, today I want to talk about the Lasso. And, the Lasso stands for least absolute selective shrinkage operator, something like this. And as you see, Professor Tipshirani has compared different paradigms such as support vector machine, lasso and elastic net, and random forest. As you see, lasso and elastic nets, they have very, very good interpretability and feature selection, as well as it is automatic process. So that's why we are interested in Lasso, because, for example, if in real world P is very, very bigger than N, I mean the feature size in the design matrix X, we have N by P, and so N is number of records in your database, but P, for example, you have P genes or P assets, but this is historical. N is historical. For example, you have 50 years of Forex or capital markets, and so when P is very, very greater than N, then it makes sense to use something like Lasso or least angle, sometimes least angle regression, and sometimes kernel dimensionality reduction methods that uses Hilbert space and is designed by Fukimizu, and other advanced methods in statistics, as well as methods that are using Hilbert spaces. Okay, in Lasso, we are trying to minimize the same cost function, except that here we add L1 norm. So we bound L1 norm, and that's why the magic happens. So in general, it could be LQ norm. Q is less than is not convex, so we don't like it. And the Lasso is convex because Q is 1 and it is L1 norm. That's why we are interested in that. And it has a geometric, I don't know if I have here, it has a very good geometric intuition behind that, because as you are going to minimize your cost functions, for example, this is beta 1, beta 2, and your cost function, this is the contours of your cost function, and suddenly at this point is not differentiable, and that's why we have problems in Lasso. We try to approximate it by subdifferential theory, which is a non-smooth mathematics. It means that we have to create around differential derivatives, and to deal with that kind of problem, we need subdifferential theory. But let's just go and see. So this is the normal least square estimate, and we introduce some bias to reduce the variance of the predicted values. So the least square estimate often has low bias. It has low bias but large variance. And prediction accuracy can sometimes be improved by shrinking the values. So the reason that we need to use something like Lasso is because, for example, you have 1 million genes or 100,000 assets. How do you want to say that, for example, you want to approximate S&P 500, SPX, and so you have lots of predictors about 505, and so you need to use some shrinkage to understand which coefficients are not equal to 0. So which coefficients are important and their corresponding covariates are important. And the Lasso is very simple. You just need to minimize this cost function subject to L1 norm. That's it. So it's very, very simple. And this is just a matrix form. And as we do in every optimization problem, we go to find the Lagrangian form. In general, you have some KKT conditions, but in analysis, we only need this one. In the next lecture, when I'm talking about selective inference, or sometimes called post-selection inference, we need this equation. We need this equation to find y, and we condition on events which ax is less than b. You know, A is a matrix, X is a vector, B is a vector. So we try to bound our coefficients, these beta. So if we could somehow bound these coefficients, then we can control them. We can do some inferential, some high-dimensional inference and understand the problem. So we just review the convex optimization here. As you see, if it is convex, that's obvious that this is the global optimality condition. And from optimality, we can say that this one is true, and we use convexity very much. And finally, you have primal feasibility condition, and complementary slackness and Lagrangian condition. And so you have many subgradients. All of these lines are subgradients. It's infinite. So we are trying to just define some derivative, because if it is non-smooth, how do you want to find the derivative of that? This could be one derivative, this could be another derivative, this one another derivative. So we have infinite derivative. And for example, for the absolute function, we have a sine function as a subdifferential. And here we want to say that this is general KKT theory, because in KKT theory, we assume that our function is differentiable. So we assume it is differentiable. But in general, here, for example, because in Lasso, we are working with non-differentiable functions, so we have to use these kind of mathematics to make some progress. Okay, and this is the geometric intuition behind Lasso, which is very interesting, one of the greatest achievements in human technology. And of course, there are many variants of Lasso, group Lasso, and many different variants. So in L1 norm is here, L2 norm is here, but and sometimes we are between L1 and L2. That's called elastic net. But this one is more useful. So this is Lasso. So we shrink, for example, beta 1, beta 2. We shrink, and then we find that, for example, from beta 1 till beta 500, for example, assets, beta 6 and beta 7, these are important coefficients. Others are just null. So we can reduce the dimensionality of the problem, and it is one of the kinds of tools that we can use for sufficient dimension reduction, as well as I have introduced it in my previous videos. And we try to control the complexity by that coefficient, by this bound, so that if we control bound, then we can understand. This is sometimes called budgets. I've heard some people say this is the budget constraints. And so here the complexity, we control the complexity. In bias variance trade-off, this is the complexity, and we always reduce the bias, but the variance increases. That's why we have, if we add the bias and variance, that is the expected error. So this is the optimal solution that we are interested in. So if that lambda is the complexity, we step by step, we increase lambda to see what is the optimal complexity for our solution. So this is just L1 norm for regularization. We could define many different, but for Lasso it's just simple L1 norm. And it is very useful in many applications, such as compressive sensing, or sometimes called compressed sensing, for compressing, for example, images from satellites. That, for example, Elon Musk has 1,000 satellites, and we want to compress these images. So we have, for example, 2,000 pixels, 2,000 features, and we reduce it. So it is much more advanced way of talking about, for example, Fourier is just a simple thing here. Fourier is for old technology, but Lasso is for the new technology. And this is the cross-validation and inference that you see for each relative bound. For each relative bound, here we can define an interval, and later you will see that how we can talk about confidence interval and all statistics, z-statistics, p-values, but p-value is originally for just one test, but here we have a huge number of tests. For example, 1,000 tests. So how do you deal with that? That's why the magic of selective inference comes out, and you will see many different paradigms. And the best of them, I think, is Tibshirani's approach, which is very, very general, with less assumptions and restrictions and stuff like that. So it's so flexible to work with. Oh, this is the fun that I was talking about. So you reduce the training error, but you increase the test error, and this is the optimal complexity parameter. For example, here lambda is equal to this one is enough. And okay, thank you very much.